Before we start. All right, so let's do a few problems. This one says two large rectangular aluminum plates of area 150 centimeters square. 150 centimeters square is roughly half the area of this sheet. Okay. Face each other with a separation of 3 millimeters between them. Okay. So here are these sheets, there's 3 millimeters. So if you're in between, how do these sheets look like to you? Infinite, right? Okay. So the field would be that produced by an infinite charge sheet. Okay. All right. The plates each face each other with a separation of 3 millimeters between them. The plates are charged with equal amounts of charges. It seems like that should be plus or minus 20 nanocoulombs. The charges on the plate face each other. Find the flux through a circle of radius 3 centimeters between the plates when the normal to the circle makes an angle of 5 degrees. All right, so I'm going to draw the plates as thick plates. And all right, so here's a separate plate. If I throw a bunch of positive charges on this plate, they will distribute, the positive charges will distribute like that. Okay, they want to get, the corners will have a higher density, but that's how they'll distribute. Now, if you throw a bunch of positive charges here and negative charges here, and the way you do that is, again, like I said, if you connect a battery like that, that's how you can throw a bunch of negative charges there, and that's a capacitor connected to a battery. We'll talk about this 2 chapters from now. If you throw a bunch of positive charges here, and we've thrown equal number of positive and negative charges here, this is how they distribute. Not like that. Why do you think this is happening? They were going to pull towards each other, and the goal is to make electric field 0 inside here. And that'll do that distribution. Okay. All right, so when you charge a capacitor, here's something that you're learning. Okay. What do they want to do? They want to pull each other. So you got to prevent them from pulling each other. So you got to have some kind of a stop, an insulating stop. So when you charge a capacitor, it's like a stretched spring. So what does that mean? You stored energy in there when you charge a capacitor. Okay, so we'll learn all of that. So again, all right, so while we're here, we can do that. We might as well do that. Okay, so here's a battery. What is a battery? What is a battery?
It's a source of voltage differential.
So a battery is an energy store of energy. When you go to a store and buy a battery, what you're buying is this much energy. So when you charge this capacitor, what did you do? You moved this energy, some of this energy from here to there. Why did you move the cheese from here to there?
If you're going to use it,
Well, why couldn't you use it from the battery?
it's less efficient.
No, it's you cannot create or destroy energy. Right? So what this does is, this guy is able to release his energy very fast. You want to release energy in a billionth of a second, you got to use this guy. This guy is slowpoke. He'll release his energy over minutes and hours. You want to fire a laser in Star Wars, You gotta use a capacitor to fill. All right, but again, I'm just giving you a preview for the next chapter. Okay, so this is how the charges distribute. The plates, an equal amount of charge. So this is Q minus Q. And sigma, the charge density here, is Q divided by area. Okay. And what is the area of the face? 150 centimeters square. Okay. Each other. Find the flux through a center. Now, okay, I'm just going to quickly state the result. The electric field here in between, electric field is sigma by epsilon naught. Sigma is the surface charge density. See, from this plate, if you had a plastic sheet and you had charge distributed like that, sigma, this electric field was E by 2 epsilon naught. Okay. This field is twice the surface charge density because you see this field here was 0. So all that field you can think of it got in between the plates. Okay. So this field is sigma by epsilon naught. There's a lot in that problem. I'm just going over it quickly. All right. So what is it that I want you to find? The charge on the plates, each other. Find the flux through the circle of radius 3 centimeters. We're going to find the flux through this radius 3 centimeters between the plates when the normal to the circle makes an angle of 5 degrees with the line perpendicular to the plates. Okay. So what we're going to do is find the flux through this area, and this area makes an angle of 5 degrees. Okay. So the flux through that plate is E dot area. E area cosine 5 degrees. Okay. E is sigma by epsilon naught. Okay. So this area is area of the plate. Okay, so Q over area of the plate, epsilon naught, and this area is that area times cosine 5. So there's two different areas going on. All right. So now we can calculate the flux. Okay. By the way, what are the units for flux? Units for electric fields are Newton per Coulomb, and you'll see that that's also equal to volt per meter. Newton per Coulomb, meter square. Okay. All right. So now let's put in these guys. So So the flux is Q is 20 nanocoulombs. The area of the plate is 150 centimeters square, and each centimeter is 10 minus 2 meters, so that's 10 minus 4 meters square. Epsilon naught is 8.85 into 10 minus 12 Coulomb square, Newton meter square, by R square. R was, the radius was 3 centimeters. Cosine 5. Okay. Let's take care of powers of 10. See, this is 10 minus 4, that cancels with that 10 minus 4. This is 10 minus 12, that, so you get 10 to the 3 on top. Newton per coulomb meter square. 20 into pi into 9 into cosine phi. 150 into 8.85. Okay. So let's do this. Okay, what did you guys get? I hit the wrong key.
774 coulombs per cubic meter is the,
774?
would like someone back me up, there's, I use the E function a lot.
Yeah, I don't like to use the E function.
I
I
don't,
got .424.
Hmm?
I don't.
Yeah, I got
Yes.
4.24 times 10 minutes, 424, 424.
That's what I looked
Yeah.
at, yeah.
Just
Yeah.
spoke up a minute ago, everyone's in agreement.
442?
424. 424.
Yeah, that's what I was getting. Instead of 8.85, I hit 8,000 or something like that, so that's what happened. Instead of the point, I hit a comma. Okay, anyway, it doesn't matter. You guys all know how to use a calculator, except your instructor, so.
I put one number wrong,
What's that?
I put a 4 instead of an 8.
Okay. All right, so again, we calculated the flux through there. So what you've learned is in the parallel plate capacitor, charges collect there. And again, what is the driving principle? You want the electric field to be zero inside there. No matter how thin your aluminum sheet is, it's got a thickness to it, okay? And so on. And as we suggested, the electric field here is almost that of an infinite sheet because these plates are so close by together, okay? A vector field is pointed along the z-axis. See that term says, what do you mean by a vector field?
It's like a bunch of vectors.
Yeah, so it's like a,
Vector fields.
huh?
Could be a electric field, could be a river, which is a vector field.
Right, exactly. Think of a wheat field, there's a wheat plant everywhere, just like that, there's a vector everywhere, okay? So a vector field is pointed along the z-axis. Find the flux of the vector field through a rectangle in the xy plane between A and that. Do the same through a rectangle in the yz plane. Leave your answer as integrals, okay? Okay, so at every point, so as you go further and further along the x-axis, okay, so you see from x and y equal to 0, the magnitude is infinite. So we won't drive there. So the vector field is pointing like that. And it's falling off, the strength is falling off, okay. and so on. So there's the vector field, and I've drawn it only in the xy plane. What happens as you increase z? What is happening to the vector field? It's independent of z. So you can draw a bunch of nails here on this plane, and you can take that plane, and you have the vector field everywhere. Okay? All right. Find the flux of the vector field through a rectangle in the xy plane between x equal to a and b and y equal to c and d. Okay? So the flux will be the fluxes of the vector field is the vector field dA. Okay. Now dA is this area. What we'll do is we'll be a little smart about drawing the area. dA. This vector is in the k direction, in the z direction. Okay. So this is equal to V is alpha x square plus y square k hat, and dA will be dx dy k hat. Okay. So k hat dot k hat is 1. So this vector field is alpha x square y plus y square dx dy, and x goes from a to b and y goes from c to d. So there's your flux. Okay. Why are they asking you not to do the integral? Because it's hard. All right. All right. Part B, do the same through a rectangle in the YZ plane. So the YZ plane. There's the area vector. And that's pointing in the I direction. So the vector field would be k dot I dy dz, and that's 0. And you can see that from the diagram. No vector penetrates that. Okay? Okay, consider the uniform electric field that, okay, so there's the, what is the electric flux through a circular area of radius 2 meters that lies in the xy plane? Okay, so the flux is E dot area, and what is the area? XY plane pi r square k hat. So if the area lies in the xy plane, the area is in the k direction. Okay, so E dot that would be equal to, so only the k term survives, so you get a 3. Okay. All right, I'll write it 4j plus 3k into 10 to the power 3 dotted with pi r square k hat. So Newton Coulomb meter square. So 3 pi r square into 10 to the power 3. So that's 412 pi. Okay. The electric flux through a cubical box, 8 centimeters on the side is that much. What is the total charge enclosed by the box? Okay, so is charge inside divided by epsilon naught charge inside. Okay. So total charge is epsilon naught is 8.85 into 10 to the minus 12 coulomb square Newton meter square, and the flux is 1. And you can see all the units cancel. So you get okay, 10 nanocoulombs. All right, let me do this one first. A vector field E, not necessarily an electric field, is given by that. Okay, so it's pointing in the z direction and 3x squared. So as you go further and further out, the strength is increasing. Okay, and so it's increasing like that. All right, let me draw the vector field. It's 0 there. So that's how it looks like. Okay. Calculate E dot N, where S is the area shown below. Okay, so the flux is E dot dA. E is 3x squared k hat. What is the area element?
A squared.
Dx dy k hat. Okay. The area, this area, dA. Okay. So k hat dot k hat is 1. So 3x squared dx dy, and dx and dy go from 0 to a, 0 to a. So Okay. So a to the power 4. All right, so we'll do this. These will get messy, so I might just tell you the results on some of them. All right, so this problem's a total charge Q is distributed uniformly through a spherical shell. So you're distributing a charge Q through a shell like that. So what is the shell made of?
And
In insulator. Okay. And you're uniformly distributing. Okay. And this is R1, R2. All right, let's find the field first for R less than R1. All right, if there is any field at all, this is, so if you're inside, you would think that the field would be in this direction if there was a field, okay? Away from the positive charge. And if it's from the symmetry of the situation, at a given distance, the magnitude should be the same and it should point inside, like that, right? You draw imaginary Gaussian surface, calculate the flux, that would be negative, that should equal the charge inside divided by epsilon. What is the charge inside? 0. So this field has to be 0. Okay? So inside the field is 0. Did you guys understand that? So you draw any Gaussian surface, okay. So another way to state this is you can draw any surface, and for every surface this is 0 because the charge inside is 0, and so the only solution is E is 0. Okay. All right, for case 2, for R between R1 and R2. All right, so now the electric field from the symmetry of the situation. So you just saw that if you have a symmetric charge distribution, the field inside is 0. Okay, so so it stands to reason that now if you're trying to find the electric field at this point, what you can figure out is that this guy will not give you any electric field. Only this guy will create an electric field. Okay, the field due to these charges will be 0, and the field due to these guys will be pointing in that direction. All right, so let's call that E. Okay. And Mr. Gauss tells us that's equal to Q inside by epsilon naught, and this is E dot dA inside by epsilon naught. This field is has the same magnitude and it's constant, and well, we'll pull it out, and E dot dA is just Q inside, epsilon naught, and all these area elements add up to this area of surface area of the sphere. Okay, R is the radius. So this is E times 4 pi R square equal to Q inside by epsilon naught. What is Q inside? That's the charge here. How do we calculate that charge? The total charge is Q, okay? And it's uniformly distributed, so we'll calculate the charge density, then times this volume, okay? Did you guys understand that? Okay, so we're saying if I take a bunch of charges distributed in this room, you can calculate the charge density, and then I can calculate the charge in this volume. Yep. Okay. I'm going to calculate the charge inside first. Okay, the charge, so it's equal to the charge, volume charge density times the volume inside. The volume charge density is total charge. What is the volume of this shell?
All the shells, whatever the outside volume is, minus whatever the inside.
Very good. So the volume of this basketball minus the volume of this baseball. Okay. So 4 pi by 3 R2 cubed minus R1 cubed. Okay. And so the volume inside is the same thing, 4 pi by 3 R cubed minus R1 cubed. Okay. And let's see, does this have the right limit? See, Q inside, this is the charge Q inside. Okay. If R were to become R1, what is the charge inside?
If R were to become R1,
R1 is this radius.
right,
If R were to become R1, what is the charge inside? 0. If R were to become R1, this would be 0, the charge would be 0. Okay. What if R were to become R2? What would the charge be? Q. If R were to become R2, this will equal, the charge inside will become Q. So it's got the right form, okay? So there we go. So the electric field is, Q inside divided by 4 pi epsilon naught R squared. Okay, so this inside charge is acting like a point charge, okay? So what we are saying is the electric field like there is due to this charge, which is acting like a point charge, okay? And you see, you can extend this argument to there as well, to this surface. And once you're outside, it behaves like a point charge with that total charge. Okay. So in between there, let me put that expression. So E equal to 1 over 4 pi epsilon naught. Q inside was Q into R cubed minus R1 cubed divided by R2 cubed minus R1 cubed over R squared. Okay, this was the charge inside. So for R between R2 and R1, this is the electric field. Yep. And that was this expression. Okay, this is the charge inside. Yep. Just messy expressions, but just using the Gauss's law. A long silver rod of radius 3 centimeters has a charge of minus 5 microcoulomb per centimeter on its surface. See, they already told you that. You take a solid silver rod, throw a bunch of charge on it, and it'll reside on the surface. Find the electric field. So we'll use capital R for that. Oops. So micro lambda is minus 5 microcoulombs per centimeter, and we'll convert this to minus 5 microcoulombs. A centimeter is 10 to the minus 2, so that's 500 microcoulomb per meter. Okay. Find the electric field at a point 5 centimeters from the center of the rod. Okay. So we're finding electric field. This is 5 centimeters. And we'll lean on the result that we saw too. Yeah. 2k lambda over R. K is the Coulomb's constant. So 2, and that's 9 times 10 to the 9. Newton meter squared by Coulomb squared. Lambda is, so the electric field will be this is a negative charge, so the electric field will point like that. And I'm just calculating the magnitude of the electric field, 500 microcoulombs per meter, and divided by R, 5 centimeters. All right, that's 10 to the 3, 10 to the 5, 10 to the 7. So 2 into 9 into 5 divided by 5 into 10 to the 7 Newton per Coulomb. 18. So the electric field is 180 into 10 to the 6 Newton per Coulomb. find the electric field at a point 2 centimeters from the center. What's the electric field inside the rod?
0.
0. All right. Can you say anything about this electric field?
It pulls towards the rod?
I'm sorry?
It pulls towards the rod?
Okay, what is the strength of this electric field doing?
It's greater than 3 times 10 to the 6.
Right, so you couldn't put that much charge, it would spark. Hmm. So maybe that should be nanocoulombs. Yeah. Right, I'll do this problem and then I'll just state the result on this other problem, okay? You'll need this for the next chapter. All right, 2 parallel conducting plates, each of cross-sectional area 400 centimeters square, are 2 centimeters apart and are uncharged. So you have 2 plates and they're uncharged. If a trillion electrons are transferred from one plate to another, what are the charge density on each plate? The electric field between the 2 plates, okay? So the charge is n times E, and the charge here is n times, it's negative n. So you took a trillion electrons from here and put it there. Yeah. And this charge is, and so the charge density is Q over area is N times E over area 10 to the 12, and the charge of each electron is 1.6 times 10 to the minus 19 coulomb, and the area is 400 centimeters square. Okay, so this is 10 to the minus 2, 10 to the minus 17, 10 to the minus 5. .6 divided by 4. 0.4, so 4 times 10 to the minus 6 coulombs per meter squared. And that's the charge density. And the electric field between the plates is E sigma divided by epsilon naught. So, is this good?
Yes.
Yes. So the point is, see, the more charge you put in the capacitor, the more energy you're storing. And you'd like to store more and more energy. What is limiting is sparking between the plates. That limits the maximum amount of energy you can store. So you can store this much charge on this. Okay. So for instance, well, yeah. So in big cities, you can run city buses on storing energy in capacitors. So every stop you go, you can charge it in 20, 30 seconds. You can charge a capacitor very fast. Okay? And then you can run them. The advantage of capacitors is you can recharge them millions of times without ruining them. A lithium-ion battery you can recharge only about maybe 500 to 1,000 times. And a capacitor you can charge much, much faster than a lithium-ion battery. So this is a great solution for those. Yeah. All right.
What are they charged by?
Hmm?
What are they charged by when they stop? You mean like when they go back to their home dock, or like when they're stopping at bus stops?
They're stopping at bus stops.
Are there like the electrical pads that they have sometimes?
I will show you a picture because these are great. Hmm?
I'm very interested.
Yeah. They've had these in China for a while. There.